Hey guys, want to talk to you today about conductors and insulators and resistivity. And so as we go about this, there are some things, some materials in life that will conduct electricity and some that where electricity is very hard to get through it. And so obviously something like a wire, electric fence, and when we did our chemistry, we found out that metals are very good conductors. There are some materials such as rubber and sort of these non-metals that where electricity does not easily flow through them. So there's a bit more resistance there, and and whether those electrons flow is based on resistivity, and that's where we want to go today. That's what we want to be able to calculate to make further predictions about whether materials are good conductors or not. Okay, so we've already looked at this idea before, but it's really the atomic structure that determines whether something is a good conductor or whether it's an insulator. And so if something is going to insulate, if we're talking about insulators, those electrons are held tightly by the nucleus of those atoms, and so they're not able to move as easily. Whereas if we look at conductors like our metals, their electrons are not held as tightly, and so they're a little bit more free to roam around, and they're a little bit they're in a better position to flow. They're not held as tightly like we just said, and so they can move around. And as soon as we get that flow of electrons, that current of electrons, then we're going to call that electricity. Okay, so when we did circuits, these electrons are only going to flow when there's a complete circuit and when we have that energy source. And so if we kind of think of electrons as if we think of the battery as a magnet and we have our electrons, they're kind of through the law of charges. If we have a negative charge, the negative terminal of a battery and an electron, those are opposite charges. So the electrons get pushed out of the negative terminal, and if they're negative and we have a positive terminal, if we go back to the law of charges, there's a force of attraction there, and so they are moving around in that direction. Okay, and we want to talk about resistors today, and so there are a variety of uses for resistors. One way is to slow things down. Sometimes if the current gets going through our circuit too fast, it might make whatever we're designing too powerful, whether it's maybe the wheels on a electric car are spinning too much. Maybe we want to dim the lights a little bit. We can use resistors to slow the electrons down, to impede their movement, and that can allow us to dim those lights, to slow some type of fan or the wheels of an electric car down. So we're going to limit the amount of electrons that can pass through. Okay, and we do this by using a resistor, and resistance, the measurement of how much we can slow these electrons down is measured in something called ohms, and we can measure it using an ohm meter or just like a multimeter like we talked about. On any type of multimeter, you'll see we can measure ohms on this too, and their ohms are kind of shown by this Greek letter omega. Kind of just looks like a circle that's not really closed off and has legs down there. The symbol for ohms is also right here as well. It's a Greek letter. So copper would have a very low resistance, and so the electrons can easily pass through. They're not being held back very much. Whereas something like tungsten, even though it's a metal, it has high resistance, and so the electrons really slow down in a material like this. Okay, so when they move through resistors, they're going to release some energy. And so if we think of something like tungsten, where it's a metal that is highly resistive, when we get our electrons hitting this metal, they're releasing some of their energy. And they can't move forward fast enough, and some of that energy would get, in the case of tungsten, that little filament in an incandescent bulb, it gets released as light and heat. And so, yeah, when my sister was a kid, she used to have like the easy bake oven, and it was just powered by a light bulb. And so things would bake in like this toy oven just by using the heat off of a light bulb. And that's those electrons releasing their pent up energy and it being given off as heat and light. And it also kind of explains, like, after you guys have been gaming for a long time, if you put your hand on the Xbox or PlayStation, if it feels warm, or your computer or whatever it is, it might feel hot. And a lot of these electrical devices, that's one of the dangers, is because in any type of electrical circuit, some degree of resistance is happening. And whenever that happens, those electrons are releasing their pent-up energy, and in this case, heat can be given off. And it can become dangerous if things get too hot. It can lead to an electrical fire. Okay, so there's this mathematical relationship between voltage, current, and resistance. And there are three formulas that kind of relate the same idea. We can calculate resistance by taking voltage and dividing it by current. We could also find voltage by multiplying current and resistance, and we can find our current by taking our voltage and dividing it by resistance. So one of your jobs is whenever you get into a question about Ohm's law, we might need to use, one of these three formulas. So it's your job to pick the correct one. And typically what the question is asking for gives you a bit of a clue, and then you can pick the appropriate formula and use it. And make sure you guys are showing all three steps on any type of question like this: your formula, substitution, and answer. So let's just go through one quick example when calculating Ohm's law. So this question is saying, what is the resistance of an electric heater if a current of 10 amps runs through it when it is connected to a 120 volt outlet? So it's asking for what is the resistance. So if I flip back a slide, this formula right here allows me to find resistance. So I'm going to pick this one to use. And so I'm going to start first mark. I'm going to write down my formula. Resistance equals voltage divided by current. I'm going to make a substitution. 120 volts divided by 10 amps. And then I'm going to get 12 ohms. And I'm done. So I know this is kind of a funny symbol to start writing, but that's what it looks like. So yeah, we see resistors in everyday life. One might be some type of electric heater. So we're just gonna use a highly resistive metal, run electrons through it, run electricity through it, and they're gonna release their energy as heat. And we already talked about the tungsten filament in a incandescent bulb. There's also something called variable resistors, and so that is, it basically depends on, like if we had a resistor this big, we might only use a little bit of it or a lot of it, depending on how we turn this dial. and it allows us to like dim lights and change speeds on fans and this sort of thing. Okay, some factors that can affect resistance. Length, the longer the wire, the more resistance we are going to have. So if you have a choice of using a 5-meter electrical cord or a 50-meter electrical cord, maybe take the 5 if you want to be energy efficient. Area, so if the thicker the cross-sectional area of that wire, the less resistance it will have. You're giving those electrons more room to flow. And temperature. The warmer it is, the more resistance there will be. And so, yeah, in Alberta, in the winter months, those electrons are moving along with less resistance than in the summer if we're talking about our power lines. Material, some metals are better than others at conducting electrons, like we've already talked about. So copper, silver, these types of metals are very good conductors, where something like tungsten isn't conducting electricity as well. That's it. Take care.